You're standing on a city street at night. An ambulance rushes past you. Notice what happens to the sound. Your ear registers a sharp, high-pitched wail as the vehicle approaches. Then, the moment it crosses your path, that pitch noticeably drops into a lower register. But your hearing is deceiving you. Up on the roof of that vehicle, the physical device generating the noise is screaming at one constant frequency. It never actually changes its tune. What you are experiencing is the Doppler effect, the mathematical change in a wave's frequency based on the relative speed and direction between the source and the observer. To understand reality, we have to look past the subjective limits of human hearing and analyze the objective geometry of the wave itself. Imagine stripping away the city, the road, and the air. We're left with a stationary object in a void, radiating sound waves. Because it sits still, there's a constant distance between each wave crest. That rate of impact is its frequency. Now, propel the object forward. The emitter races after the sound waves it just created, displacing the starting point for every new cycle. At the front, the waves are packed tightly together, compressing the space like a coiled spring, resulting in a higher pitch. Behind the object, the emitter flees from its own sound, stretching the distance between each wave like a pulled elastic band. Fewer waves hit per second, creating a lower frequency. The wave's physical geometry is literally deformed by motion, making the pitch shift a structural reality. An observer in the path of the approaching object is bombarded by those tightly packed compressed waves, hearing a high pitch. Move that exact same observer behind the object. They are struck by the elongated waves and hear a much lower frequency. As the ambulance rushes toward you, you intersect that compressed high-frequency front. The moment it passes, you are instantly submerged in the elongated wake. Perceived pitch depends entirely on where you stand relative to that geometric distortion. These same principles of wave geometry dictate the behavior of light as it travels through the vacuum of space. Light, like sound, is defined by its frequency, the number of wave crests that pass a point in a given time. This shared structural nature means light waves are subject to the same physical deformation when a celestial source moves. If a star or galaxy is hurtling toward us, its light waves bunch up, compressing into higher frequencies. In the visible spectrum, we see this compression as a shift toward the color blue. When a source is speeding away from us, its light waves are stretched out into longer, lower frequencies. This pulls the light toward the red end of the spectrum, creating a redshift. These spectral bands show the distinct fingerprints of light emitted by stars. Scientists analyze the precise positions of those vertical black absorption lines to measure exactly how far the light has been stretched. When we observe distant galaxies, those dark lines are almost universally shifted toward the red. The light is elongated, indicating that nearly everything we see is moving away from us. A moment of wonder. Because galaxies in every direction exhibit this same stretching, it suggests the fabric of the universe itself is actively expanding. Redshift serves as a precise cosmological ruler, providing measurable proof of how fast that expansion is occurring. The laws of physics are an absolute invariant. The same geometry that governs the wail of a city